Welcome to our webinar on powering the IoT. My name is Peter Spies. I'm the manager of the marketing work package of the European project Enables. Enables is a project focusing on building up European infrastructure for powering the Internet of Things. Today is the final webinar of a series of 16 webinars on the topic of energy harvesting, energy storage, and micropower management. These webinars were carried out over the last 3 years. The series of webinars was organized by the project Enables. Today's webinar is a best of webinar where we present some highlights of our research activities and of the transnational projects. The transnational projects are projects which were done during the project runtime with external partners. Presently, you see the agenda of today. So we will start with a short wrap up of the project, which will be done by Mike Hayes. He's the Enables coordinator. Next talk will be by Raphael Salot. He will report on the joint research activities which were achieved during the runtime of the project. Then we will continue with some outputs from the transnational access projects. The first one from Tyndall National Institute on aircraft tracking devices and on smart wound care patches. Then I will continue with the transnational project on customized thermoelectric power supplies. Then my colleague Felix will continue with the topic of RF harvesting for temperature sensors. Then we will make a short bridge to the topic of virtual tools for energy vibration energy harvesting experiments by Francesco Cotone. And finally, we have a last transnational project report from Guillaume Zavelli from CEA Lytton on thermoelectric characterization. So now I'd like to pass over to my colleague and the Enables coordinator, Mike Hayes. Please, Mike, go ahead.
Okay, thanks, Peter, and welcome everybody, and thanks for taking the time to join us today. So what I'm going to do is I'm just going to start with just a little bit of an introduction as to what Enables is, what the challenge is, and maybe just a high-level overview of some of the results. So let's see, hopefully this works. So can everybody see my screen? We should see Introduction to Power IoT Challenge. Can everybody see this?
Yes, we can.
Okay, very good. Okay, so you've heard me use the term there, the Power IoT Challenge. I'm sure most, if not all of you, are familiar with this term. But really, this is the problem and the opportunity that we're trying to address out there. We need to find a way to make batteries last longer in wireless IoT edge devices. So the question is, how do we do this? Well, there are 3 ways to do this. The obvious one is, of course, to make better batteries. Give us batteries that are smaller, more compact, that supply more energy for a given volume. But there are other ways of making the batteries last longer as well. And this includes reducing the power consumption of the IoT device. You know, these IoT edge devices typically comprise sensors, microcontrollers, transceivers. And the third methodology we look at, is, of course, is energy harvesting. That is the use of ambient energies, using naturally occurring heat, vibration, and light energy around us and converting this to electricity, and using this as our power source. So this is where Enables comes in, and where you get the alignment between the opportunity and the challenge and the vision that we have in Enables. So Enables was all about, and is all about, building an ecosystem to power the Internet of Things. And it's done by the 11 partners you see on the bottom of the screen here. So we have Tyndall, Fraunhofer, CEA in France, and IMEC in Netherlands, all giving access to our facilities, as well as doing joint research activities under the banner of Enables. Furthermore, we have 6 other research institutes, KIT, we have Polito, National Institute of Physical Systems in Perugia. We have Southampton, and we have University of Bologna in Italy. So these are the 11 partners.
Mike, I still see slide number 2.
Slide number 2. Yeah, hopefully you should be okay. So I think I've moved on to slide number 3 now. I'm seeing enables vision and quick introduction, no? Is everybody else seeing the same problem? At the moment on my screen, I'm seeing slide.
I'm still on
Slide number
step 2
3.
as well, yeah.
Okay, 1 second now. Let me see what's going on here.
So you're also not in presentation mode, if that helps.
Okay, let me just see why it's not working. Okay, let me stop sharing and start again.
Yeah.
And apologies for this. Hopefully it works this time. Okay, can everybody see slide number 2 now?
Yeah, we see number 2 and we see your cursor moving. This is a good sign.
Okay, yeah. I have an extended screen, so I've just disconnected the extended screen, so hopefully it works now.
But now we see a black screen.
Yeah, so do I. Okay.
Yep.
Okay, we have it now.
Okay, now I think.
Okay, well, hopefully this works. Okay, so yeah, this is slide 3 then. So this is what I was explaining. Hopefully everybody was listening. This is the ecosystem that Enables has been building. You can see at the bottom of your screen now the 11 partners involved in Enables, the 4 transnational access providers, Tyndall, Fraunhofer, CEA, and IMEC, and then the other 6 research providers. We've got KIT, Polito, National Institute of Physical Systems, which is Perugia, Unibo, and Southampton. Can everybody see this now?
Yeah.
Yeah, okay, very good. Okay, so that is the ecosystem that we've been building in Enables, doing collaborative research amongst ourselves and opening our doors to do collaborations and to do feasibility studies for others. And really, at a high level, what we're trying to do in Enables is we're trying to drive system level thinking and drive optimization of energy harvesting micro power management solutions via collaborations, via ensuring interoperability of our solutions, and making sure that the platforms we developed are standardized as well. So the 2 key activities under Enables are its transnational access, and that's provided by Tyndall, Fraunhofer, CEA, and IMEC, which is effectively opening our doors to give people access to our laboratories and to our people to do feasibility studies. And you will find this very well documented in many of the previous webinars that we've given. The other activity we have amongst all 11 partners then is joint research activities. And these are internal collaborations amongst the Enables partners, creating system optimized and application orientated solutions, developing de-risked and standardized methodologies, and creating library parks. And this is done by the partners, as I said, listed below. Again, more information can be found on these 2 types of activities on our website. And here is the vision then that we're trying to create. Most people understand the concept I'm showing there. These are kind of what we call the enabling technologies: energy harvesting, energy storage, micro power management, and system integration. And I think most people understand the various IoT applications we're trying to serve. So we have developers, users, suppliers, and integrators doing things such as Industry 4.0, smart mobility, assisted living, home care applications, utilities, renewable energies, and so on. But we have, throughout Enables, discovered that there's a key and a missing middle layer between the technologies and the end applications. And it is, as I show here, we need to also bring into our ecosystem the kind of stakeholders that we're showing here. People who are developing and integrating sensors, wireless communication systems, ICT technologies, MEMS, and indeed NEMS technologies, people developing low power electronics, people developing microcontrollers. And it's really only by getting all of these collaborators working together that we can truly figure out how do we develop solutions which are system level optimized and give us maximum battery life. So won't labor on this. We've done this in many previous webinars, but very, very briefly, the Enables Transnational Access Program was all about giving free of charge access to our people, our tools, our equipment to do feasibility studies, whether it's a paper study, some sort of initial simulation or characterization, or whether it's development of an early prototype or doing some system level optimization experiments. We've also under Enables got a virtual access program, which gives people access to what we call real-life vibrational energy harvesting sources. And this has been developed by our partners, University of Southampton and Perugia. And this is open to everybody. It's open to industry and academia, whether you're a researcher, a developer, a system integrator, material or device developer. So just a quick summary of what we've achieved in Enables. We're on the last couple of weeks of Enables. It's been a journey of just under 4.5 years. So we have built an ecosystem of 555 subscribers to Enables, and we're very proud of this achievement. Our target was 500, and to exceed this, particularly in the difficult COVID area, we consider it to be very, very substantial achievement. We've had 176 inquiries from 36 countries. We've had 71 transnational access programs approved, and we've given access, virtual access to 35 subscribers. We ran an online conference open day on the 19th of May last year, and details on that can be found via the link here. We've run in Perugia 3 summer/winter schools, 2 of them being physical and 1 of them being virtual. We've in recent times, now that we're all recovering from COVID, we've given face-to-face presentations at APIC, the world's largest power electronics conference, Fierce Electronics, and we've been one of the co-founders and sponsors of EnerHarv. This is a biannual international energy harvesting conference. Again, more information on that can be found on the Enables website and indeed on the EnerHarv website. We are still active. We're going to be given a presentation next week at IoT Week in Dublin in Ireland. It's an international IoT conference. And then in the US at Sensors Converge at the end of June. We have, as of today, we will have 16 webinars completed and available online. We have published 13 newsletters. So anybody who's been subscribed to Enables will be seeing these coming to their inbox every 3 or 4 months. We have published 75 papers and we expect around 10 more. And anybody who's been following us on social media see that we've been quite active promoting all of the activities that you see above and more. We've also been, and this is an important activity, been contributing to various international roadmap activities. Apologies for the acronyms here, but this stands for Energy Components and Systems Strategic Research Innovation Agenda. This is an EU funded activity. PSMA is the International Power Sources Manufacturing Association, so it's a Power Electronics Association. And then associations such as the IEEE have IRDS, which is the International Roadmap for Devices and Systems. And they also do a heterogeneous integration roadmap activity, and we've contributed to all of these. So these are very, very important guidelines for people in terms of what technologies are emerging, and most importantly, how do we integrate these technologies to solve problems and indeed to avail of many IoT opportunities that are out there. We also, very importantly, published a position paper last year, and we're happy to report that Cordis have published some output on this in 6 different languages, and the link is there for anybody who wants to access this, outlining the relevance, the context of the position paper that we have here. So this position paper is a very, very important statement that we've made in Enables, underlining the importance of the Power IoT challenge and indeed the opportunities that come from it. And anybody who has not seen this, I would strongly encourage you to go and have a look at this and see why this work is so relevant for all stakeholders that we have shown there. Okay, so that is my opening introduction. So I'll pass you back now to Peter to introduce the next speaker on the next part of the agenda. Thank you.
Great. Thanks a lot, Mike, for this wrap up. Now I'd like to introduce my colleague, Rafael Saló from CEA-Leti. He will give you a report on some highlights from our joint research activity which we achieved during the course of the project. So, Raphael, please.
Thank you, Peter. I will try to share my screen.
Yes.
Can everybody see my screen now?
Yeah, it's seen and it's also in presentation mode. Great.
Okay, good. So good afternoon, everyone. So as mentioned by Peter, I will try to put the stress today on some highlights for the different building blocks we work on in the frame of the Enables project. So as also mentioned by Mike during his short introduction, in order to have some efficient power supplied, we work on different subcomponents, meaning energy harvester, energy storage components, but also micro power management and some simulation tools. So today, for each of these topics, I will illustrate the development we perform by one work per thematic. So I will begin by the energy harvesting part, and we decided to push the stress on the work done by a team of Francesco Cotone from the University of Perugia on nonlinear electrostatic vibration energy harvester. So as you know, in order to harvest energy, there are different options. You can either use some photovoltaics energy harvester, some thermoelectrical harvester, but you can also try to harvest energy from vibration from the outside world, and it's a good way to recharge some battery and have some longer lifetime for the batteries. So in the frame of the Enables project, regarding vibration, the work was based on nonlinear electrostatic energy harvester that are particularly suitable for MEMS and NES fabrications with some tunable electromechanical coupling. But in the frame of Enables, what we developed was the use of some 3D printing technology to fabricate this kind of components at a low cost compared to the standard microelectronic MEMS and NEMS fabrication that require some clean room facilities. So you have on the right of the picture some illustration of some silicon MEMS and of some 3D printed components that allows for high flexibility and also high performance in reduced volume and at millimeter scale. So the main results obtained during the project was first to have some theoretical and numerical modeling of the behavior of such components. So it was not done only in Perugia, but also in collaboration with the University of Southampton. Based on this modelization, some prototype, so based on 3D printing, has been done. So they were made both of resin and PLA. PLA stands for polylactic acid, which is a thermoplastic polymer charged and can be used as electrodes, and integrated also with some graphene flex. And all these materials have been implemented to manufacture some 3D printed energy harvester. Then, after that, some lab tests have been done. You can see on left picture illustration of the vibration test. And what was very interesting in this work is that real vibrations were simulated using some large database that are currently available, so allowing to have a very good prediction of the behavior of such components in real-world applications. And the performance appear at the end of the day to be very good compared to standard silicon MEMS generators. So you have here some example of the main results of the modeling and simulations that have been performed. And on the next slide, some electrical results measured on this kind of components. And you can see that some maximum power of 1.6 milliwatts were achieved at a frequency of 170 hertz and with an acceleration of 0.2 gram, which is quite nuts for such a component. So that was the first highlight dedicated to the energy harvesting parts. Now we will move to the energy storage part, and I will, in this part, present some works on innovative polymer electrolytes, a work that was performed at Politecnico di Torino in the team of Claudio Gerbaldi. So as you may know, solid-state battery is a very, very hot topic nowadays, and is a very promising solution to power the next generations of different components, but mainly EV, electrical vehicles. So since it can lead to very efficient energy storage components, with also some key advantages, both in terms of safety, but also allowing high voltage operations and allowing to have very performant components. So when we talk about polymer electrolyte, they need to be compliant with different metrics. For sure, the first one is to be very efficient from an electrical point of view, and the characteristic that is looked for in this case is a very high ionic conductivity at room temperature. Also, what is very important for an electrolyte is its stability regarding the positive and negative electrodes of the battery, and the interfaces between these different materials. And finally, of course, what is expected is to have a high number of cycling, discharge, and recharge, and also to be compliant with upscaling for industrial manufacturing. So lithium polymer electrolyte is an electrolyte that can answer to all of these requirements, and can lead also to some lightweight, but also shapeable components, and with some low-cost fabrication. So in the frame of the project, a lot of work has been done on this topic, leading to a high number of high-level publications, so more than 15 published articles in this for this thematic. So based mainly on new materials for polymer electrolyte, including room temp ionic liquid, for instance. And as you know, the ideal electrolyte needs to have a ionic conductivity. I have already mentioned this point, but also to have a high lithium transference number. And the ideal electrolyte is to have both of these criteria at green, let's say. So in the next slide, you will see some different examples of work done, and that led to the different publications. So in this one, you have example of advanced single ion conducting polymer electrolyte that was obtained by modification of single ion connecting polyelectrolytes. And that was obtained by designing novel block copolymers, which combine one block that is responsible for ionic conductivity and another block that is done to improve mechanical properties and the electrochemical stability. So thanks to these two blocks, it is possible to meet all the requirements. And you have an example of the specific capacity obtained and the cycling number, the evolution of the capacity with the cycling, showing a stabilized cycling with high voltage cathode, so in an all solid state configuration. And it's important to know that in the roadmap of the battery, it's looked to work with high voltage cathode and also with metallic lithium in negative electrode in order to improve the volumetric energy of the next generation of batteries. So second example is the use of a protic ionic liquid-based electrolyte, so with lithium metal batteries. So as previously mentioned, lithium metal batteries is also very important in the roadmap. And once again, very good results in terms of cyclability was obtained, and it was the first proof of concept of this kind of electrolyte in a battery, lithium battery configuration. On top of the, let's say, the performances of the material, what is very important also is to have some good interface between the electrodes and the electrolytes. Otherwise, some additional resistance can appear and be very detrimental to the good behavior of the battery. So what was achieved here was to develop an architecture with some in situ polymerization and cross-linking of the polymer. So you have on the left side of the slide some explanation about the process that was used, and here some picture of the electrolyte on top of the electrode and the good electrical behavior of this components once again. So it's very important in terms of electrical performances, but also in terms of scalability of the process for manufacturability. So now, after this two highlights on components, energy harvester, energy storage, now we will move to another part, which is also very important since it deals with the micro power management. Indeed, when you have the energy stored in the battery, for instance, then you have to power the loads. And to do that, you need most of the time to use some DC-DC converters to obtain the good voltage to power the loads. And the study that was done here at the University of Bologna in the team of Aldo Romani is to improve the battery lifetime by using some high efficiency DC-DC converter. And the idea here is to reduce the pulse that are seen by the batteries in order to improve their lifetime. And that is done by some DC-DC converter that use 2 stages to decouple the battery from pulse current. So the first stage is what is called a decoupling stage, using a buffer capacitor, and then a second stage, which is typically the DC-DC conversion stage, using a buck-boost architecture, and that allows to power the load with the right voltage. So here you have an illustration of this DC-DC converter, and also on the fact on the voltage seen by the battery on the right part of the slide, and you can see that thanks to the use of the buffer capacitor, the voltage of the battery moves only in a very smooth domain, and avoid to see some pulse currents, which is good for the lifetime of the battery. And the efficiency of the DC-DC converter is improved by the use of a stepwise conversion, and typically a relative improvement of approximately, let's say, about a few percent, about 8%, was obtained with respect to single stage one-shot conventional architecture. Now I will move on the last part related to simulation tool, and to have some energy model for wireless sensor network. So the idea here is to have some simulation tool that allows to predict, let's say, both the lifetime of a component, but also to predict whether they are self-sustainable in terms of energy, regarding the energy they can harvest, store, and what is needed to power the loads. So it has been some wireless sensor nodes have been designed and measured with different solutions architectures. And you have the example of this three architecture that are mentioned here in the next slide. So the first architecture is based on the LoRaWAN soil moisture sensor node, and you can see on the left the use case of this kind of sensor node. So the time where the sensor is a sleep mode, the time where the sensor is acquiring some data, the duration for the data transmissions, and so on. And you can see that then with this simulation model, it was possible to predict the lifetime of the system based, for instance, on different LoRa spreading factor. In the second case, which is a -7 temperature floating sensor node with some PV harvesting, same kind of simulation was done, and it was thanks to that it was possible to show that this kind of solution was self-sustainable, assuming a transmission period of 10 seconds, and with some photovoltaic energy harvester. And the last one was a use case to illustrate the interest to have a wake-up radio solution for this kind of sensor node. And so you have here the illustrations with and without wake-up radio. And you can see in the table that thanks to this wake-up radio, you can have some self-sustainability for some photovoltaic harvesting motor actuator node. And also you can reduce the number of minutes between two motor actuating requests in the case of thermoelectrical energy harvester. So that's all what I wanted to share today. I hope it was a good illustration of all the work that was performed in the GRA from Enables. And once again, there was a lot of other work performed in the frame of this project, but we had to make a choice today for this webinar. Thank you for your attention.
Thanks, Raphael, for that great overview and for these exciting highlights from our research topics. So we have time for one question. So to the listeners, if there are any questions, please put them in the chat and we will answer them if there is time available after each talk. So if there are any questions to Raphael, please put them in the chat right now. If this is not the case, then I will pass over to Ivan Ahern from the Tyndall National Institute. He will present two outputs from transnational projects. One with the title Battery Life Improvements for Aircraft Tracking Devices, and the second one, Thermal Harvesting Opportunities in Smart Wound Patches. Please, Ivan, go ahead.
Hi, can you hear me?
You're a little bit distorted.
A little bit distorted, is that better?
No, not really.
Okay, 2 seconds there now, let me check my microphone.
Yeah.
It should be okay. This is the one I usually use. It's still fuzzy.
It's still a little bit fuzzy, yeah.
Is that better? I'm a bit closer to the mic now.
Not really. Perhaps that's my problem.
No, I'm hearing it as well. Yeah, Owen, I think if you just try and stay as close as you can. It was a little bit louder. There's still distortion there, but it is louder when you're close. So
Seconds, let me move.
Just
let me
stay close to the microphone.
Yeah, no problem. 2 seconds there now. Is that any better?
No, same. Yeah, I'd say just continue. Just try and stay close to the microphone.
Yeah, 2 seconds. I'm gonna move my position a little bit. That's a bit better.
It's a bit louder, yeah. Okay, I'd say just continue.
Okay.
We can
Can you
see
see this?
yeah, we can see the first slide, yeah?
Yeah, perfect. Two seconds, it's just transitioning over to slideshow. It seems to have frozen. Hello?
Hello, we can hear you.
Perfect, 2 seconds there now.
Yeah, now it's in presentation mode. Now we see you. Yeah, now it's again in presentation mode. So that looks good. That looks good. The slides are changing. Everything's fine.
Good. Thank you very much. Okay. Let's start. Hi, my name is Ola Hearn. I'm a research engineer with Tyndall National Institute, and I'll be presenting some of our team work on Enables. There are two projects from Tyndall's work on feasibility studies that I will present. The first project is related to tracking cargo in aircraft in more detail than is currently available, and how we can use energy harvesting and ultra-low power electronics to extend the battery life. And secondly, a project that looks at smart wound care and the opportunity for thermal harvesting in this area. Aircraft tracking of items in transit is relatively primitive in this current state. In the spirit of Industry 4.0 and the Internet of Things, we want to provide more information on this section of travel as remotely as possible. Items are scanned in at a receiving point and scanned out at its destination, but we are missing vital information in the transit of the cargo. A universal load device is a storage container that is used to transport items in aircraft, as seen in the slide. Swiss Airtainer, the industry partner, want more information on the transit section of the ULBs, and this requires sensing, processing, and active power to communicate conditions of travel, safety, and the position to interested parties. For this feasibility study, we were looking at sensing things like temperature and humidity, 3D acceleration, a 3D compass, pressure and sound, electrical power signals, as well as looking at relevant ultra-low power methods of tracking that could be utilized by an application like this. Things like RFID and BLE can be utilized for short range and manual tracking, whereas LoRaWAN and GPS and NB-IoT can be used for longer range tracking. The study produced an investigation into the power consumption of current solution, analysis of the actual requirements, and reviews of what ambient energies are actually available in specific application of ULBs, which can vary due to the fact that they're underneath the carriage. So things like light and heat aren't as abundant. The development of the analog front end represented in the block diagram shown here is one of the main focuses of development, as well as innovative algorithmic use of sensing capabilities for given situations. Non-linear requirements in IoT present a huge opportunity for us to optimize our systems algorithmically. The outcomes of this study were the development of an appropriate energy harvesting schedule or architecture for the given application, an innovative control and detection circuit for activating and deactivating certain aspects of the system when not needed, a significant reduction in power from 10 milliamps to 50 micrograms with automatic dependent surveillance broadcasts, a 300% rise in battery life with a smaller battery, and can be powered by a 50 by 50 millimeters squared solar panel. Power can be reduced even further from 50 micrograms to 11 micrograms if ADS-B is not needed. This study shows the potential opportunity for energy harvesting and wireless sensing to impact the transport of goods meaningfully. It also shows the usefulness of the Enables program to the academic half of the partnership by allowing us to conduct these feasibility studies and literature reviews on relevant industrial applications. For the second half of my presentation, I'll be reviewing the work Tyndall has completed with ICON on smart wound care. Smart patches present a clear opportunity for energy harvesting, power management, and ultra-low power wireless devices. ICON's business focuses on the active electrical stimulation of wounds to promote healing. And smart wound care is also based around the monitoring of pH of wounds, as this can be indicative of healing, of the healing stage of the wound. The main focus area of this project were firstly to investigate the capability of healing via electrical stimulation, and secondly, to investigate the opportunity to harvest thermal energy from the patient's skin. I'll briefly discuss e-stimulation or electric stimulation on slides 8 and 9, and show a theoretical plan that we presented to ICON for slide 10. So just the ability to use e-stimulation was looked at from two angles: muscle therapy and wound care. The benefits to muscle therapy were reportedly accelerated injury recovery, muscle training and massage. The benefits to wound healing, enhancing cellular motility along the edges of the wound, with generally positive outcomes to healing. So it's slightly quicker healing times. There's a lot more research and trials required to actually delve into this deeper, and this is something that we reported back to ICON. The theory behind e-stimulation is that the wound's healing uses a current of injury, which is the motility of the cells around the edge of the wound. And electrical stimulation can enhance the skin battery or the energy held between the different layers of skin, because there's a slight potential difference, and that's where this current or cell motility is derived from. And slide 10 is an example of the possible power management style or pulsed or duty cycle stimulation, a number of variations that are recommended to ICON to develop further research in this area. The investigation into whether or not TEGs could be used to provide more energy showed a number of roadblocks. Wound care can often be most important on low mobility patients, people who do not move much and do not develop much heat. Therefore, the temperature differential can be quite low. If under clothing, the temperature differential is even smaller due to lack of convection, and different age groups and individuals have a huge variation of heat flux. Most literature shows us the use of a heat sink being used on the wrist with larger areas being utilized. And though these findings are not ideal, the point of the feasibility study is to help us understand the roadblocks in our way and how we should navigate around these. How do we get more energy from a small area without the use of heat sinks? How should we characterize TEGs at smaller temperature differences? How do we make solutions robust enough to deal with the individual heat flux differences, which can be so large? This study is an example of an opportunity for a large industry like medicine to truly think of ultra-low power operation, and an opportunity for us to understand the trade-offs and how realistic settings are often more complicated and nuanced than we would like to think. Thank you for listening, and any questions are welcome. I'll try to answer them to the best of my ability. Thank you very much.
Thank you, Ivan, for that 2 use cases from our enabled transnational projects.
No problem.
Thanks a lot. Are there any questions? Please put them in the chat. So presently this seems not the case. Then I like to pass over to the next presentation, which is actually my own one. I like to report on a technology which is using temperature variations to produce electrical energy, and my talk is called Customized Thermoelectric Power Supplies. I will share my screen. So you should see my first slide, is that right?
Yeah, we can see it.
Okay, thanks a lot. So in my talk, I like to focus on doing energy harvesting from thermal variations, which is a relatively new way of harvesting electrical energies. So variations over time of heat source can be used with a so-called thermal capacitor. A thermal capacitor is a mass with the highest possible thermal capacity. The concept of such an harvesting system is shown on the right side. So we're using a standard state-of-the-art thermoelectric generator. We connect one side of the TEG with the thermal capacity, with the thermal mass, and the other side we use a standard heat sink and connect it to the ambient temperature. So if we have an increase in temperature of the ambient air, then a certain amount of heat is also flowing through the thermoelectric generator and is heating up the thermal capacitor. Due to the flow and to the thermal resistance of the thermoelectric generator, we have some time delay of the temperature of the thermal capacitor. And that leads to a certain temperature difference between the ambient and the thermal capacitance. If we have a cooling down of the ambient energy, the process works the other way around. So we have a decrease of the ambient temperature. So a given part of the heat from the thermal capacitor is flowing through the TEG in the other direction, so flowing to the ambient. And we have a cooling down also of the thermal capacitor, but we have a time delay also between the temperature of the thermal capacitor and the ambient. And so in this way, we generate a a localized thermal gradient over the thermoelectric generator. So typical application areas for such systems are all objects and areas where we have temperature variations. For example, airplanes during takeoff and landing. I will show you an example later on. Another application area are industrial machines during heating up or during cooling down. Or a third application areas are any objects in an outdoor environment, because in an outdoor environment, I can use the thermal change, the temperature change between day and night. Actually, some of the measurements I will present today are from an enabled transnational projects, which we did with the Imperial College. We used their harvester design in the first step and optimized our power management. So a promising application field for that technologies are airplanes during takeoff and landing. What you see on the measurement diagram here is the temperature, the ambient temperature at the outside of a plane during takeoff and landing. So during takeoff, we have a temperature decrease up to -40 degrees C, and during landing, we have a temperature increase up to +20 degrees C. What we have done here is we have generated that thermal change in the temperature, climate chamber, and we have put the whole harvesting system also in that climate chamber. And the harvesting system is built by a heat sink, by a thermoelectric generator between heat sink and thermocap and the thermocap. And what you can see here is actually the temperature of the thermocap in green and of the heat sink in blue. And you see during the cooling down, we have a temperature difference between heat sink and thermocap. And this is actually where the thermoelectric generator is located. And due to that thermoelectric thermal difference, we have an output power of the thermoelectric harvester, which is shown here in red. At the reversal point, we just reverse the two temperatures of the heatsink and the thermocap. And during the cooling down process, we have also a thermal difference between heatsink and thermocap, but it's the other way around. And this reason and the point, the challenge of this system is that we have a reverse polarity of the thermoelectric gradient. And this is the reason why we need a bipolar power management system, which is actually a DC-DC converter, which can work with positive and with negative input voltages. And so we can use the positive and negative thermal gradients, which are available in that thermal capacitor. This is actually the circuit we are using at Fraunhofer IIS. This is a low cold start circuit with a very low cold start voltage of 35 millivolts. And this cold start is achieved by the combination of a transformer and a zero threshold MOSFET. And with that low cold start voltage, we are also able to use even the smallest thermal gradient, for example, here at the starting points or here at the reversal point of the temperature. So actually here is then the same measurement as before, but here we're showing the output energy during that full cycle of 2 hours. So during that full measurement cycle of 2 hours, we were able to harvest 5.2 joules. This is nearly 50% of the theoretical maximum of 10.8 joules, and with that energy we were able to charge a 5 farad supercapacitor from 2.3 volts to 3.2 volts. So another use case for that thermal harvesting systems are day and night variations. With the help of these day and night variations, we could generate electrical energy and power, for example, outdoor sensors or also industrial sensors. Of course, this output power in such an application is always depending on the season and on the geographic location. So, of course, different day and night temperature variations are available. I am showing here 2 examples from Germany. One is a measurement from August, where we have between day and night a thermal gradient or difference in time over time of 20 kelvins. And the same here is in October, where we have a temperature day-night difference of 10 kelvins. Of course, here it is obvious these systems work best during summer. during longer periods where we have a constant temperature, energy storage device have to be used to power a potential application. So this is then a harvester design we did by our own at Fraunhofer IIS. You can see here the heatsink. Below the heatsink, you will find a standard thermoelectric generator. And in that black box, there is nothing more than water, because water is a very good thermal mass. It also has phase change properties, which help facilitate these harvesting systems. What is really critical on this design is the isolation of the thermal mass, because we want that only the heat is flowing through the harvester and through the heatsink into the mass and vice versa. And we have to avoid any heat flux on these other areas. And so it's very important to have a very good isolation on all the 5 areas of this cube. Of course, the thermal mass is strongly influencing the potential power output, but regarding outdoor application, large geometries in such a form here are not a real problem for a potential application. So here we see the measurement results. The time period is, of course, important to get the highest thermal change, and so to get the most power output. This is the reason why we chose here the time period from 6 a.m. to 8 a.m. in Germany, because here we have a significant increase in temperature. At 6 a.m. we had 0.1 Kelvin per minute. At 7 a.m. we had 0.05 Kelvin per minute. And between these 2 hours, this is the output power we could get with the harvester. And the power is roughly between 100 and 700 microwatts. So the total energy we could harvest here during these 2 hours were 3.3 joules. So summarizing my talk, I wanted to show you that thermal capacitors enable the use of temperature variation, and these temperature variation can be used to power any kind of IoT sensors, of wireless transceivers. Of course, the key is an efficient power management, which provides a very low startup voltage. And especially, it has to provide a bipolar input stage so that we can use positive and negative thermal gradients. Most effective is that system, of course, during summer, during critical periods of the year. So in Germany, that would be December, January. The power could be buffered with a battery, which is charged during summer with the help of that system. And summarizing the technology, so depending on thermal gradient and volume of the thermal capacitor, several hundred microwatts are possible to be harvested with such a system. Okay, thanks a lot for your attention. So are there any questions in the chat? I have to see. This seems not the case. Then thanks again. And then I like to pass over to my colleague, Felix Essingholt.
I think there was one question.
Yeah, sorry. Got it. The thermal electric was black. It was. No, it was not on the sunlight. It was not under sunlight. We have, yes, there is not a paper, but we have a presentation done at the last PowerMEMS. If you Google the PowerMEMS agenda from last year in December, there was a presentation from my colleague Markus Pollack, and we did a presentation and explained mainly the circuits, but I think from Imperial College, there should be some more presentations or papers regarding the technology. Okay, then I'd like to pass over to my colleague Felix Essingholt from Fraunhofer IMS in Duisburg. He will give a talk about RF harvesting for temperature sensing in harsh environments. Please, Felix.
Thank you. Can you hear me and see the slides? Hello, can you hear me and see the slides?
Yes, we can hear.
Okay, great. Okay, hi everybody. My name is Felix Essingholt. I'm going to talk about RF harvesting for temperature sensing in harsh environments. Please excuse my voice. I'm just coming down from the COVID illness. I hope that it doesn't break and I don't run out of breath this talk. So I will talk about, like I said, RF harvesting, especially in RFID systems. RFID stands for radio frequency identification and usually relies on a reader that transmit energy to one or more transponders that in turn harvest the energy and respond to queries that the reader sends. So it's always that the reader starts the communication, provides the energy to the transponder powers up via the energy and then answers the queries. It does so by changing its internal load impedance and therefore scattering different amounts of energy back to the reader, which can then be detected by the reader and demodulated. This means that we can have quite a cheap, in terms of energy, quite a cheap communication. So we don't have to harvest much energy at all to get a communication running. And this enables us to do quite small wireless sensor systems. Okay, so why would we use RFID for this use case? There are lots of different applications using different sorts of energy harvesting, as we saw before. But using RFID, we can actually provide quite a lot of energy. So it's not energy harvesting in the typical use case where we use ambient energy. We actually provide the energy. And the reader in the UHF band, for example, can provide up to 2 watts of power. ERP. So depending on the distance to the transponder, the energy will obviously decrease, but in most cases, we can actually employ RFID sensors without the use of any batteries. Since we don't have to rely on batteries, we actually have quite a lot of availability for different applications. So we can employ the sensors in different harsh environments like high temperatures where usually batteries might degrade or be damaged, or in low temperatures where batteries just flat out wouldn't work. This means that we can basically negate lots of problems with the use of batteries in outdoor applications, for example. Also, since we actually transmit a lot of energy to the transponder, we can achieve higher read rates. We don't have to wait a long time to accumulate a lot of energy and then send a data package. We can do it in a matter of seconds, basically. And this is actually one of the use cases in one of our transnational access projects, where the project partner wanted us to do a temperature probe for cooking inside of ovens. So you can imagine, like in this sketch here, that you have a probe that is put inside of a piece of meat, for example, or a piece of bread, and therefore you can measure the temperature inside of the meat and monitor the cooking process. Since the temperature of the oven obviously is quite high, it's up to 260 degrees, the customer didn't want us to use any batteries for the fear or the risk that the battery might be damaged and leak into the food, therefore contaminating it and ruining the food or poisoning the customer. So this use case actually is just like I described before. And so we have harsh environments. We don't want to use batteries, and we have small distances which we can couple with electromagnetic waves. And this is what we came up with. So we designed 2 antennas, one for the reader and one for the transponder. The top one here is for the reader. This is a bow tie antenna, which is basically a high bandwidth antenna, which is quite important for this application because the different states of the oven, like the temperature or the loading states, as in how much food you put into the oven, can actually detune the antenna. And therefore, to counteract the detuning, a higher bandwidth of the antenna is quite helpful. For the transponder, you have the meander dipole, which is just chosen because of the size that we were limited to. It is matched with the loop and has 2 long, kind of like wires running to the RFID IC. That is due to the fact that we wanted the electronics to be inside of the meat to not to be exposed to the completely high temperatures of up to 260 degrees Celsius, only to the cooking temperature of less than 100 degrees Celsius, so that the electronics might still work. And we also designed the circuitry for this application. The project partner wanted us to use multiple analog temperature sensors. So we used 4 PT1000 temperature sensors, which were connected via transistors, so they can be switched on and off to a microcontroller, which then samples the voltage over the temperature sensor. So we can basically digitize the temperature sensor or the temperature value in terms of voltage level, which will then be transmitted over SPI to the RFID front end, which then will be read by the RFID reader. We designed the system. Sorry, we designed the system in CST MicroF Studio. So the antennas and the high frequency components were simulated and optimized in the 3D field simulator, CST MicroF Studio. And then it was imported into Altium Designer, where we included the circuitry and the, basically the circuitry, and designed the layout around it. Then we milled the PCB in a PTFE substrate, so that it is actually it can withstand the high temperatures, and placed the components, soldered them on top of it. And this on the right hand side here is the finalized prototype, so it's encased in a steel rod, which will be then pushed inside of the cooked good, or the meat, or the bread, as we saw in the sketch. And as you can see, the RFID chip and the other electronics will be inside of the rod, and therefore they will be inside of the meat. Therefore, the temperature that they will experience is limited to the temperature below 100 degrees Celsius, basically. To verify the working principle of this system, we used a heat gun to basically change the temperatures of the sensors. And as you can see here, this is the heat gun that blows air to the demonstrator, to the prototype. And below this box, there is a RFID antenna that is read by this RFID reader. Basically, we continuously read the data while changing the temperature. And you can see here in this graph that the temperature differs depending on the time, and of course, depending on how much we actually blew the air on top of it. There's also a slight offset for the red curve here, which means that the voltage divider for one of the sensors was out of tune with the others, but this is something that can be calibrated in further steps. We also tested the readability in an actual oven or in a climate chamber to see if that would influence the readability of the RFID transponder, and it worked fine. So in conclusion, I think this TA project actually showed quite a few promising things for RF harvesting, especially in harsh environments, highlighting the RFID technology. And I think this was quite an interesting project for highlighting. If you have any questions, please feel free to ask. And otherwise, thank you very much for listening.
Okay, thanks, Felix. So I'm giving a few seconds if there are any questions to pop up. Okay, seems not the case so far. Then thanks again, Felix.
Thank you.
And I'd like to pass over to Francesco Cotone from Perugia University. He will report.
Hello. Hello, do you hear me?
Yeah, we hear you.
Okay, I'm going to share my screen.
Yeah. Francesco's title is Virtual Tools for Vibration Energy Harvesting Experiments. Please, Francesco, go ahead.
Thank you very much, Peter. So I'm going to make a summary of the work about virtual access resources that we have developed during the Enables project. Okay, after a brief introduction on vibration energy harvesting, I'm going to show you some details about the vibration database we have developed also together with the University of Southampton, and also about the integrated tools and simulators that are available online for researchers, and some a case study just to show an example of the usage of this kind of service. Okay, as you know, one of the source of energy that can be captured from the ambient and this is quite interesting compared also to other sources, is the vibrations. Vibrations are everywhere, but one of the main characteristics of vibration, of natural vibration or artificial, is that they are the power is mostly located at low frequency. So we are talking about frequency below some kilohertz. So for these reasons, it is important to design a vibration energy harvester specifically for the source where it is applied. And so we have developed a real vibration database that is a repository that includes all kinds of vibrations that comes from researchers, also from our university, measurement testing. And so all of these vibration can be downloaded or used for experiments in lab and also for simulations. Okay, so as you may know, there are three main techniques for converting energy from mechanical vibration into electricity. There is electromagnetic or inductive, then there is a piezoelectric, the use of piezoelectric materials, and also electrostatic or capacitive. And here it is shown some of the examples of regenerators. Usually these generators are of the size of few centimeters, but also there are generators developed with the MEMS and NEMS technology nowadays that are below also few millimeters. But the main challenge is to be able to capture energy at very low frequency with a very small size of device. And this is quite a big challenge because, as you may know, the natural resonance of a small device is very high. So it doesn't match the natural frequency. Here you can see the main page where it is possible to have access directly to our vibration repositories. One is provided from University of Southampton, the other one from University of Perugia. And after registration in the Enables platform, it is possible to have access freely on this resource. And in particular, the two resources are quite complementary. So we have all kind of vibration coming from automotive or bridges or infrastructures, domestic appliance, human and animal movements, and machinery. So it is possible also to search inside, for example, in this case, our website, to have to make a quick search of by keywords of the type of vibration or the source that we want to get, and also we can see all the main characteristics of this data set. For example, the sampling frequency by which it is the vibration is logged, and also the length of the signal, and also the spectrum, the power spectrum. We have also developed some categories. So we have grouped all the vibration sources by categories. As you can see here is the example of vibration logged from a cat walking, so and with a collar. And you can see the power spectrum and frequency, also the time series below. Okay, and also University of Southampton have a quite rich vibration database, and also where it is possible also to get information about the type, about the main characteristic of the vibration, and usually they have very long data set and rich data set. Okay, so now I'm going to show you the simulation toolset. So what we have developed during the project Enables, we thought that it was good to provide researchers with some additional tools. One of these is a simple calculator that you can have access and use to simulate an transduction independent vibration harvester. For this, I mean, by this simulator, this calculator is based on the simple theoretical model of an spring damper oscillator. So it is possible to have a first and a quick estimation of the maximum power that you can get for a certain mass and spring, mechanical spring and or stiffness, and also damping, and with an input maximum acceleration. And then there is a second tool, and also this tool, it is based, as I said, on the theoretical model developed by William and Yates. And this model is based on the simple modeling of the spring mass damper system, where the conversion is implemented by an additional damper, that is the electrical damping. So as you can see here is the formula of the power as a function of frequency and a function of all the parameters of the device. So these parameters, of course, depends on the type of transduction technology that can be, as I said, piezoelectric or inductive or electrostatic. And also, if you consider the maximum power, so if you consider that you can tune your harvester precisely on the main resonant frequency, on the main natural frequency of the source, you can get the maximum, the maximum power at the resonance that is represented by this, calculated by this formula. Okay, now the second tool is a simulator that uses a specific vibration harvester, specific transduction technology based on piezoelectric bimorph cantilever. In this tool, it is possible to select every type of signal, also getting the signal from the database. And so the signal can be a simple sinusoid or either whatever signal, like a noise or a signal coming from human movement, for example. Then you can also give as input a set of parameters, geometrical and physical parameters of your piezoelectric harvester, and run the simulation. So in the simulation provide you with the input in black, the input acceleration over time. Then you have the output displacement of the mass and also the output voltage. And also the average power is calculated over is average over the time interval that you are simulating. Okay, so here I put some of the references. Then I will provide the presentation. And then also this is based on the theoretical modeling of the equation, of the governing equation, dynamical equation of the piezoelectric device. In this case, the computer on the client side make the integration of numerical, make a numerical integration also on stochastic, of the stochastic and nonlinear differential equations. So this is quite CPU intensive, but it depends on the type of the signal and of course on the characteristic that you provide to your device. So here is a use case. If we select, for example, a data logged from a running person, as you can see here, the peaks of the acceleration are in phase with the natural movement of the people, and you can see here the displacement of the harvester and also the output voltage. And in this case, for example, for a load resistance of 200 kilo ohm, we can get out of around 1.8 milliwatts, which is okay, not very high as a power, but it is realistic considering the size, the small size of the piezoelectric generator in this case. Okay, so this data set can be also sent to a signal generator that control, in this case, a shaker, and with the shaker you can mimic the real vibration that you get from ambient source, and test, of course, in the limit of the power spectrum of the shaker, you can test your device. In this case, you can see this is a piezoelectric, our piezoelectric generator, but implemented with some non-linearities, in this case a bistable dynamical generator that can increase the bandwidth of the harvested energy. And indeed, the simulated power with the simulation was 1.89 milliwatt, while the measured power was around 2.4, and I show you in a moment also the video. It was about 2.45 milliwatts. And the increase in the powering is due to the nonlinearity that was implemented in the system. As you know, a nonlinear system can harvest energy from a wider bandwidth with respect to a simple resonance system. So this is just a demonstration of this case. So in conclusion, we through this project, we provided a service of virtual access, implementing some simulation tools and also enriching vibrational databases that can be used from researchers all over the world, also from by companies and professionals, in order to make prior to develop prototype, to make some estimation and also some use case design. And this can be very helpful in our opinion, and also the database can be in the future, in the near future, in a follow-on of the project, follow-up of the project, we can be reached with also other kind of energy sources like wind levels, light irradiance levels, radio frequency, thermal gradients, and so on. So in order to have a platform in which we can compare different kind of harvesting technologies, and also we can make some rough estimations at first before developing or making a real project of energy harvesting technology. Okay, so thank you. I concluded, and thank you for your attention, and I'm here for questions.
Yeah, thanks a lot, Francesco, for your interesting talk. Are there any questions? Please put them in the chat so that we can read them. I think we should give a couple of seconds if there are any questions are popping up. Okay, seems not the case so far. Then thanks again, Francesco.
Thank you.
And then I like to introduce the last speaker of today, which is Guillaume Savelli from CEA Litten. He will report also from a previous transnational project. His presentation has the title Thermoelectric Characterization of Thin Film Materials Obtained by Screen Printing. Please, Guillaume.
Thank you, Peter. Can you hear me?
We can hear you.
Yeah.
We can see your screen.
Okay, perfect.
Perhaps if you
sorry to interrupt, but Guillaume, but we have a question in the chat window.
Okay.
Might be worth catching that from Iman.
Yes, yes, I see now. And from Iman, yes, we have some data. Okay. Yes, it is possible to add this data. So he's saying that they have some data of energy sources, like gas flow in the source pipe. So it could be very nice to enrich the databases with this kind of data. And of course, it is possible just by a simple registration to add data, for example, from wave motion. If you have, for example, for this data logged with a specific accelerometer or whatever, you have to just send us all the details about the data logger. Okay, thank you.
Yeah, thanks, Francesco. Then again, Guillaume.
Okay, thank you, Peter. So good afternoon, everyone. I'm Guillaume Savelli from CEA Litten in Grenoble, France, where I'm in charge of the thermoelectric activity. And as introduced by Peter, so I'm going to present you a transnational access project dedicated to the thermoelectric characterization of thin film materials obtained by screen printing. So here at the context of this project, so we receive an access applications from the International Iberian Nanotechnology Laboratory in Portugal. This team works on the development and formulation of PBEC ink, which is then used for the fabrication of thermoelectric thin films by screen printing. So this study is currently performed at INL in the framework of Viviana Souza PhD thesis. And the objective of this project, the objectives were to measure the electrical and thermoelectric properties of PBAC thin films and the temperature dependence, and also to evaluate the influence of silver doping in PBAC thin films. So here at CE-Lithane, we have a lot of characterization tools for thermoelectric applications, both for materials and devices. And that's why they contacted us to help them to characterize their materials. So for the electrical property measurement, we use Hall effect measurement, which is 4 probes measurements, as you can see in the pictures below. So we can measure the electrical resistivity, mobility, and the carrier number at room temperature. For that, we use an holder with gold probes, as you can see here. Electrical contacts are performed with or without silver lacquer, but in this case, there was no difference. We applied a magnetic field, and generally we obtain 5% error in measurement. It can be a little bit higher for samples with high electrical resistivities. So for their samples, you can see here the Hall effects results. So as you can see, the charge carrier concentrations obtained was higher for silver doped PBAC samples. So it's quite logic due to the silver doping. But we measured a lower mobility. And so the electrical resistivity was lower for PBAC layer compared to the samples with silver doping. For the thermoelectric properties, we use ZEM3 measurement principles. So you can see the tool in the pictures. So we can, with these tools, we can measure the electrical resistivity and Seebeck coefficients from room temperature up to 200 degrees Celsius for thin films. The contacts on samples were performed with titanium and gold deposition to obtain good ohmic contact. Each measurement is performed with several temperature cycles, and they presented very good reproducibility. And with these tools, we usually obtain 7% error in measurements. So you can see here the results we obtained. So in the figure on your left, you have the temperature dependence of the electrical resistivity and the Seebeck coefficient. So as you can see, the electrical resistivity is lower for PBAC layer compared to silver doped PBAC. So it's confirmed the results obtained by Hall effects. And also, you can see that we obtain higher Seebeck coefficient for the sample doped with silver compared to PBAC. And as you can see, we can obtain very high Seebeck coefficients up to 850 microvolt per Kelvin, which is a very high value for thermoelectric materials. And so on your right, you have the temperature dependence of the power factor. So the power factor is defined here. It is defined by the square of the Seebeck coefficients divided by the electrical resistivity. It indicates partially if a thermoelectric material is good or not. And so here you have the comparison between the both samples. And in first, as you can see, we obtain a peak around 140 degrees C. But except for this peak, you can see that we don't have any influence of silver doping on the power factor. So in this case, we obtain a very high Seebeck coefficient, so up to 560 microvolt per Kelvin and 860 microvolt per Kelvin at 140 degrees C for PBAC and silver dot PBAC respectively. A peak was obtained for the thermoelectric properties around 140 degrees C. And also regarding the power factor, we don't see any influence of silver doping. So these results were very interesting, and so a lot of communications is planned to present this kind of results. Two abstracts were submitted, one for the next European Conference on Thermoelectrics that will be held in Barcelona in next September, and also to the International Virtual Conference in July. And also a paper is currently in progress and will be submitted in the journal Nanotechnology. Okay, thank you.
Thanks a lot. Thanks a lot, Guillaume. Are there any questions to Guillaume? Please put them in the chat. Okay. This seems not the case so far. I think I have some delay, but presently there are no questions. So thanks again, Guillaume, for your talk. Now I'd like to hand over to Mike Hayes for some final words of today's webinar. Mike?
Yes, thanks, Peter. Can you all hear me okay?
Yeah, I can hear you, can see your screen.
Very good, good. All right, okay, so let me go into presentation mode. So hopefully it works this time. Does this work?
Yeah, presentation mode.
Okay,
Great.
very good. Okay, so thanks everybody for staying with us for so long. But as you can see, we've achieved quite a lot in the last four and a half years, and this is only the tip of the iceberg. These are just some examples of the kind of work that we've been doing under the JRAs and the TAs. So just to wrap up, I'd just like to make you aware that we have many other use cases, many of which can be seen in previous webinars or on indeed on our website. We have done 71 transnational access projects in total. Go onto our website and you can see here a screenshot of some of one of the activities, for example, that we've done here. And also, I mentioned the webinars. Several of the webinars cover good examples of the use cases. So if you want to see further examples of these, please check out our website via the TA offerings and the previous webinars. Finally, one other very good source of information is the position paper that I mentioned earlier on during this webinar. This is something that we would recommend to anybody who's interested in the Power IoT opportunity and the Power IoT challenge. The link is here and you can find it on our website as well. In a previous webinar, we've given some insight as to what's under the hood of this, but we do describe at a high level some of the transnational access activities and some of the joint research JRA activities. And it's really all about innovation and impact. What are the key technology innovations that we're generating, and what is the associated system level impact that we can have in terms of extending the battery life of devices. And as we asserted at the start of this presentation, you know, we've put ourselves and enabled at the epicenter of this infrastructure, the ecosystem that we're putting together, getting people to collaborate to make these devices have a longer battery life. Okay, we've done this before, but just very briefly, here are some testimonials from the position paper that I just mentioned. I do not expect people to be able to read the small font there, just mainly look at the text we have there in italics. So for example, one testimonial said with the RF harvesting technology, we plan to expand our portfolio and serve a much bigger market in the future. Another testimonial said with the realized prototype, we aim to optimize power harvesting for millimetric frequency range IoT devices, where there is a surge of interest for commercial partners And one other SME one was that this will result in materials that can deliver more energy in real life applications. Okay. Other ones then we had are US SME said that this gives us a solid basis for characterizing and optimizing power consumption of our next generation of devices. Another SME said this technology will lead to a commercialized product that increases the safety of assets and goods and ensures on-time delivery. And one further SME said the feasibility study showed us that careful power management at controlled intervals would enable us to activate self-cleaning sensors. All right. So some very nice stories there. Please contact us or dig into our previous material if you want to learn more about these. So to wrap up then, where do we go next? You know, so we want to keep the Enables ecosystem alive. So we want to continue to inform, educate, and guide the ecosystem that we've been building so carefully over the last 4 or 5 years. Even though the project finishes in 2 weeks' time, we will retain the Enables website and the database. And we do plan to apply for following funding. We are awaiting for an open call from Horizon Europe regarding research infrastructure. So we'll be looking at that eagerly to see how can we leverage from all of the work that we've done and the repositories we've created, and indeed the ecosystem of partners that we have created. We will continue to promote the outputs of Enables, and we would kind of use our Enables position paper kind of as our kind of vision as to what we're trying to do with the ecosystem that we have been building. Okay. And last but no means least, we need feedback from you good people. We want to hear from you. How can we best serve the Power IoT community? So please give us feedback. You know, you have all our contact details. You can contact us by email, contact us on social media. You can contact us, giving us feedback to today's webinar. It's only by getting feedback from you that we understand how we can best serve the Power IoT community and give people technological solutions that give us long battery life for all these IoT applications. So that is it. Thanks everybody for listening, and we welcome any final questions either now or you can send them to us offline at your own time and your own convenience. Thank you. So back to you, Peter.
Yeah, okay. Thanks for the final last words, Mike. So I have not much to add, only to thank all the speakers for their presentations, for the preparations. Of course, thanks especially to Nicolas and Paul for the marketing and for the housekeeping and providing the Zoom call. And of course, thanks to all the attendees for today's conference, for visiting today's webinars, but also for visiting any of the previous webinars which took place over the last couple of years. And of course, thanks for assisting the Enables project and program in any kind and any way. So thanks a lot to you. Thanks for your participation and have a nice afternoon. Thanks a lot. Bye-bye.